We're looking at this polynomial, x to the power 6 plus 8, and our job is to factorize this polynomial. Factorize according to the fundamental theorem of the algebra. The key to factorizing this polynomial, of course, finding all of the roots of this polynomial. And that's something we actually practiced extensively on Wednesday. Because if you look at this polynomial, if you equate this to 0, if you equate this to 0, it will be the equation like so. X to the power 6 equal negative 8. And that's the roots of a complex number. It's something which we know how to do now. We have to bring this number to the exponential form. Here's my exponential form. Remember, in the exponential form, absolute value or modulus must be positive. So I have to somehow take care of this negative. And the way to take care of this negative is to make the e to the I pi for this negative. In fact, if you let me zoom out a little bit, that's this blue vector. That's my number 8. This is a number 8. Oh, negative 8, sorry. That's the vector which represents number negative 8. Now, okay, I think it's big enough. Now, if I go after my roots, we know how to do that. Here it is. We have 6 different solutions. We know how to produce them. First, we take the 6 root out of the number 8. It's a very quick computation. 8 is a 2 to the power 3. When you take the 6th root, it will be 2 to the power 1/2, or just root 2. And then goes your exponential. You divide your argument by 6, this argument by 6. And then you add up your revolutions, 2 pi I k on 6, or if we cancel out 2, it will be pi k I on 3. Here's your roots. I'm not going to elaborate too much on this one. We did it quite extensively on Wednesday. I think I have a few pictures of these roots here. Yeah, I do have them. Yes, here we go. So let me just picture these roots here. These red vectors, that's the roots. All of them, all 6 of them. Let me just find, here's my k. Here's my k. K takes values between 0 and 5. 6 roots. If I picture them, here they are all of them. It's a z0 vector. z1. Z2, Z3, probably I should zoom in a little, let me just make it bigger. Z3, Z4, and the last one is Z5 over here. Right, so knowing all of these roots, let me factorize my polynomial. Here's the factorization, look at this. I'll give you like a condensed version of that. So here's my factorization, not really much different from the general statement on the slide above. So I take my x and subtract all of these roots. I'm not going to actually put the values in. It's too much to write, even when you do it on the computer screen, and I don't want you to copy this. It's just, I mean, like it's too much of an effort and wasteless, actually, wasteful effort. So here's my roots, all of them here. I'll make an F and I put all of them here. That's your factorization. In principle, you can replace every of these z with the value of all of these values, and that will be your result. That's where the factorization ends. Okay? So the question there, well, the actual question 25 on page 25 says factorize this polynomial, and there is this still mysterious part in the sentence there which says factorize the polynomial over C or over R. I'll elaborate on this extra bit what we mean by what we expect from you when you factorize over C or over R. Over C already we did this. That's the factorization over C. It means that every factor on the right-hand side in your factorization contains complex numbers. And that's true, actually. All of these Z's are complex numbers. All of these Z's are complex numbers. Right. Okay. However, the second part of the question asks us to factorize this polynomial over R, which means we have to produce factors here on the right-hand side. Factors here on the right-hand side, which have only real numbers. No complex should be present in there. In fact, if I ask you, could you factorize this polynomial over real numbers? One of the trivial answers should come up right away. What would be the trivial answer? How to factorize this polynomial over real numbers? What would be the simplest, the most trivial answer you could come up with? Yes, please. No, it's not. It is acceptable answer. It is a factorization, but that's not the one which is the most trivial one. Yes.
1 times.
Yes. The polynomial itself, quite a good factorization, right? Take 1 times the polynomial. What's wrong with that? I didn't put any extra constraint on my question, right? So you can just kill me with this simple answer. However, when you go after factorization in real questions, of course, we expect you to find the factors of the smallest possible degree. So for instance, here, all of the factors here of degree 1, and that's, you can't go any smaller than that. So it's the best possible one. It's the most detailed factorization ever. Now, when the question goes about factorizing over real numbers, the same extra constraint applies. You have to find the factors of smallest possible degree. Okay? So this one, this trivial one, when I say just x to this whole polynomial times 1, not really good one because my factor of degree 6, and the first which you suggested, this is the one which you suggested first, x cubed take something, x cubed plus something, also not really a good one. Well, it's better than my first one, the trivial one, but not really the perfect one because the polynomial is involved in factorization of degree 3. And the question comes, can we just lower this even further, below 3? The answer is yes, and look how we can do this. The key to this factorization over real numbers is this observation that these roots, these red vectors, look at them, they have very nice property, they have a symmetry. They all comes with a complex conjugate in pairs. For instance, this Z0 comes with a complex conjugate here. This Z2 comes with a complex conjugate here, Z3. This Z1 comes with its complex conjugate down here, Z4. And we can exploit this extra observation. Look how can we exploit this extra observation. I should have somewhere here, the way to exploit it. Here we go. Look what happens if I have 2 linear brackets like this, x takes Z0, and I factor this linear bracket with the bracket where we have complex conjugate. Anyway, look at this little thing. If you multiply these 2 linear brackets where Z0 and Z0 bar present, number needs complex conjugate, you can do normal expansion when you just multiply 2 brackets. I put the dots here. You can fill this gap without my help. The result will be something like this. Let me just check this for you. X squared obviously just comes when you multiply this x with this x. Linear term x will come when you take this x and factor with this negative Z0, or this x and you factor this negative Z0 bar. That's why you got this extra negative and these two together. And the free term, free of x term, or actually x free term, will be the product of this Z0 and this Z0 bar. That's the expansion. And when you look at this one, you can recognize something like you can actually simplify this even further. You can say here that we know that the sum of the complex number with its complex conjugate delivers real part of that complex number doubled, and that's what stands for this bracket. And we also know that the product of the complex number with its complex conjugate delivers modulus squared. Let me now move it now. I can move it and I can zoom a little bit. You see how we can exploit, now I think you can see how we can exploit this extra observation we made, that the complex numbers for this particular equation comes with the complex conjugate pairs. Because when you multiply these 2 brackets together, the result will be, look at this, the result will be something which no longer have any complex numbers in it. Because this number, the real part of a complex number, it's a pure real number, and the square of the absolute value of the complex number, it's also pure, it's actually purely positive, a non-negative number. Right? That's a trick how to convert factorization over complex numbers into the factorization over reals. The only requirement to do this trick is that the roots must come in the complex conjugate pairs. Let's just do this trick for my actual factorization here. Oh, in fact, let's just do this trick for this actual parameterization here. I think it's here. Right, so let's just do what I just said. Let's just look at these brackets and let's combine those in complex conjugate pairs. So let's just combine this Z0 with this Z5. Of course, if I combine them, I need the real part of this number. What's the real part of this number? Root 6 on 2. Yes, that's the correct one, although here I wrote a little bit different. I wrote like this, root 3 on 2. What's the length of this number? It's right here in the exponential form. That's the length of it. So when I combine in this expansion, when I combine this Z0 bracket with this Z5 bracket, with the complex conjugate, all I should do, I just have to write something like this, substitute the real part with what we have for the real part, and substitute this one with what we have for the length of it, right? Let's just do this. It should be here somewhere. Yeah, here's my factorization. Look at this. X squared, take, now comes double of the real part, root 6, that's a double of my real part, and the square of the length, which is 2. Combination of these two brackets together delivered this square polynomial. Let's just move on further. Now if I combine, I think next I should combine, if I remember correctly, this root with this root. If I combine Z1 with the Z4, again we can do the same trick. What's the real part of Z1, for instance? 0, so this term will be missing in my combination. And the length of this one is 2. So the combination will be, here we go. Finally, when you combine Z2 and Z3, similarly, the real part will be just the negative of this real part due to symmetricity. And you got your factorization. I didn't do much of the computations. Everything came, in fact, from the picture of the roots. And that's the factorization, which is purely over R factorization. And that's the best you can find. It's better than you suggested. There's no offense, but it's better. Because these polynomials, they of second degree rather than the third degree, which was suggested first. Okay? And that concludes this question. Yes, please.